Okay, optimization to minimize cost. They've given us a question. It says a cylindrical chemical storage tank with a capacity of 1,000 meters cubed, okay, so this is volume, is going to be constructed in a warehouse that is 12 meters by 15 meters by 11 meters. The specifications call for the base to be made of a sheet metal that's $100 per meter squared. The top is to be made out of sheet metal that costs $50 per meter squared. And the wall of the tank to be made of a sheet metal that costs $80 per meter squared. The first thing they want us to solve, is it possible to build the tank of this capacity in this warehouse? If so, state the restrictions on the radius. Okay, we're going to jump to the other page here. Okay, so if you recall, they said they were going to build this in a warehouse. And the warehouse was 15 Here's our warehouse. The warehouse was 15 by 12. Is that right? Yes. It's 15 meters by 12 meters. And the height of the warehouse was 11 meters high. Okay? So, what that means here is we got to think, and of course, sorry, the volume of this is going to have a capacity of 1,000 meters cubed. We need to think of what will be possible values of this. So first of all, if everything is maxed out, this is a cylindrical object. I think that's circle. Guess I can't draw a circle right now. That's okay. Let's make this box here. Okay, if we're making a cylinder and this has a width of 12 meters, what is the max radius we can have of this cylinder? 12 will definitely be the max diameter of the circle. That's right. So we have our circle here. Kind of looks like a lip. Our circle here. Our radius has a max of 6 meters. So what we're going to try to do, again, we're going to max this warehouse out to be as high as possible, and we'll have our circle again at the top of this. I know it's not the greatest cylinder, but the height will be 11 meters. And when thinking of the volume of a cylinder, remember I told you find the area of the face? Well, the area of a circle is equal to pi r squared, which means the volume of this cylinder is pi r squared, and then you just multiply by the height of the object to find the volume, times height. So we're going to find out what the max volume of this object is if we have a height of 11, which is our max height, and a large radius as possible of 6 times pi equals volume. So we're going to see if it's even possible to make something this large. So what we're going to end up with is pi times 6 squared is 36 times 11. 1244. 1244. So the max volume is 1,244 meters cubed. Okay? So if that's the max volume, that means we can definitely fit this 1,000 meters inside of this warehouse. We need to find out what the minimum radius would then be. Well, in order to do that, we take our volume formula again. Our volume formula, and we're going to set the restrictions down to radius. So pi, r, we still don't know. We're going to assume we're using a max height of 11. Okay? And again, our volume needs to reach 1,000 meters cubed. So we're going to replace volume with 1,000 is equal to pi r squared times 11. R squared is going to be equal to 1,000 divided by 11 pi. And we're going to root whatever that is. Let's figure that out. 1,000 divided by pi, or 11 pi, 28.9. And we're going to need to square root that, which is then going to give us 5.379, approximately 5.38-ish, we'll say. Okay? So that's the minimum radius we can make in order to create this capacity of 1,000 meters cubed. So our restrictions on this is our radius needs to be less than 6 meters, but also then greater than 5.38 meters. Okay? So that's a very small window on how large we can make the radius of this object. Now, we got to relate it to cost. Cost of this object, if you remember, dealt with our meters cubed, squared. In other words, we're dealing with surface area of a cylinder. So let's talk about a cylinder again. Surface area, let's say we have our circle, and then the rest of our object. Well, the top of this circle was going to cost $100 per meter squared. The base of this circle here was going to be $50 per meter squared, and the wall, I believe, was $80 per meter squared. So we're thinking about cost. Cost of this is going to be the top, base, and let's call it the middle, okay? Well, this cost is going to be whatever the cost of the top is, which is going to be our T, plus the cost of the middle, plus the cost of the base. These costs are all related to area, okay? So the area of the top, our cost is 100. So it's going to cost us 100 multiplied by the area of the top. That was our pricing. The middle was $80 multiplied by the area of the middle. Plus, and the base was $50 times the area of the base. I'm just putting those letters there so we have an idea of what that means. Well, the area of the top, C is equal to 100 times area of the circle is pi r squared plus 80 times the middle we'll talk about. We'll go to the end first. 50 times pi r squared. Same thing, top and base. The middle, if you guys remember, what this becomes is actually a rectangle. When we break it all up, we pull this out and unravel it, we get some type of rectangle. The height of the rectangle is, you could say, is the width, okay? But this length here is actually equal to the circumference of this circle. So the circumference of this circle is 2r pi, okay? Doesn't deal with r squared. Because its circumference is 2r pi times the height. So it's 80 times 2 pi r, or 2r pi. So our cost function in terms of radius is equal to 100 pi r2 plus 50 pi r2 plus 80 times 2 is 160 pi r. When we combine those, cost related to the radius of this is 150 pi r squared plus 160 pi r. Okay? So we've now dealt with our cost function. We've made an equation that talks about the area of this. So in terms of radius related to what this is going to cost us. Because we need to minimize, we're looking for slope being 0. And to solve that, we're going to derive. So C prime r, the derivative of this function, this becomes 300 pi r plus 160 pi. Okay? So we've now derived this function here. Now, the radius of this, we need this to be equal to 60 pi. Yeah, I think we're okay. Oh, you know what we did miss out? There's an h here. It needs to be multiplied by the height. I'm just going to add the h in at the bottom. Pi r technically times h. Pi r technically times h. Okay. Before we derived this, so I'm going to go back to before we derived it, there was an h involved. Now, because we want a function in reference to radius, we need to make our h some equation in reference to r. Not right now. So, our h, our volume of this, the height of it, okay, if you guys remember, our volume was equal to 2 pi r by h in this question. Sorry, not 2 pi r, but just pi r squared, not 2. So r pi, why did I write it like that? Pi r squared. I'm not sure why I wrote it like that. Times h, which means the volume of this was going to be 1,000, so we make this 1,000 is equal to pi r squared times h. This then becomes 1,000 is equal to h divided by pi r squared. Okay? So if that's our h, we're going to plug that into our equation. Our c in reference to r is now equal to 150 pi r squared plus 160 pi r, and our h is 1,000 divided by pi r squared. So now this equation is in reference to the radius. Okay, we've referred all of this to the radius of this equation. We can combine this part here to simplify at the end. C at r equals 150 pi r squared. When we multiply 160 times 1,000, what do we end up with? 3 more zeros. 160,000 pi r divided by pi r squared. Okay. Well, if you look at that, we know the pi's can cancel out to create a 1. And our r's will create just one r on the bottom. So our simplified version of this, we want it to be simple as possible in order to derive, is 150 pi r squared plus 160,000 divided by r. Thought we were missing something there. This is our cost equation. Forgot to include our height before. So again, we still have to derive this. C prime r is equal to 300 pi r. And because this is a division, we can use our quotient rule to solve this. Okay? So plus quotient, we find a derivative of 160,000. Well, that's going to be 0 times r. Subtract the original 160,000 times the derivative of the bottom, which is 1, divided by the bottom squared, r squared. Well, the top of this will equate to 300 pi r plus, this is 0, subtract 160,000 over r squared. So this is now the derivative of that. And we now have our C prime r. Okay. Well, we know we need to set this equal to 0 in order to solve this question. So 0 will give us a minimal idea. We know our slope being 0, pi r plus 160 divided by our r squared. Negative, yes, yes, yes. Because this is negative, this turns into a negative. So subtracting like that. So we're going to move this to the other side. Our goal here is to try to figure out our radius. Okay? I'm going to move 160,000 over R2 to the other side. We get 160 by R2 when it goes the other side, it becomes positive, is equal to 300 pi r. When I move r2 to the other side and I multiply, we get 300 pi r cubed. The goal is to figure out what r can be. So r cubed is equal to 160,000 divided by 300 pi. And then when you put this all in your calculator and find the cubed root of it, you're going to end up with 5.54. So we need to go look at our restrictions. Our restrictions way up here were 5.38 and 6. Are we between 5.38 and 6? Yes. Okay. So remember, we're trying to minimize cost. Oh my God, I'm losing my voice. So we're looking for when R is the lowest possible value, which is 5.38. Good. Also when it's 5.54 and when it's at max width of 6. Our cost function, the original cost function, our C at R, was 150 pi r squared plus 160,000 divided by r. When we plug in C at 5.38, we carry this out, we get 150 pi 5.38 squared plus 160 divided by 5.38. Our cost will then be $43,380. When we do cost at our tangent of 5.54, we plug it into the same equation. Our cost will be 43,344. And finally, when cost is a radius of 6, 43,631. So, to minimize cost, again, we're at our tangent point. It'll cost us $43,344 to build this cylinder if our radius is 5.54 meters. Quite a bit to the last question.